Assalamu alaikum. Can you hear my voice? Okay, firstly, I should say Eid al-Fitr Mubarak to all of you. And secondly, I should say that I'm extending the deadline of the second assignment. Some of you asked for this extension, so you can change your submission until tomorrow. The third note is that for the third assignment, is related to this slide 14. I will upload this assignment tonight, and you can do. You have the deadline of this assignment is Friday this week. Okay. In the last week, we talked about classification, and also we start to talk about decision tree approaches and classifiers, and we say that how we can create an ID tree. ID tree was is one of the first proposed tree classifiers. So we firstly start with this classifier, and now we will continue the course. Okay. As we talked in the last lecture, to create the ID tree, to partition the different attributes, selecting and partitioning the tree structure, we use information gain. But there is one main note here. What we should do with continuous valued attributes. When we are talking about nominal attributes or interval attributes, or attributes that have some categories in their values, we can easily use information gain and act based on those classification, those groups. But what we should do with continuous value, because in continuous values we have not an option for a splitting point. We have to determine the best splitting point for a continuous values. Maybe 1 point, maybe more than 1 point, but we should have to choose some split points. We cannot create a tree with continuous values. We have to split those continuous value into some areas, and then using that value, those values, those split points, to partition the data and creating the tree. To do this, firstly, we should sort all values from, for example, attribute A. Let's suppose that attribute A is a continuous valued attribute. Okay. Firstly, I should sort the values of A in an ascending manner, increasing order. Okay. Then maybe the first and the easiest point for splitting is the midpoint of A. So, for example, if I have two values AI and AI plus 1, I can choose their midpoints according to this formula as an splitting point. If I use this strategy for each pair of adjacent values, let's suppose I have 10 different values. For each of those adjacent values, I'm sorting those values in an ascending manner. Okay. Then in the space between each pair of adjacent value, I'm selecting an split point. It's a possible split point. I can choose those points, maybe yes, maybe no. Okay. But which of those attributes are better than the rest? It's the main question. I found some possible split points, but which of them are good? I should select some of those values only. To solve the problem, we say that we should choose points with minimum expected information requirement for A. Okay, so the split point for A is a point with the minimum expected information requirement. So we should define what is minimum expected information requirement. We should define it. Okay. But before of that, I should note that when I'm choosing an splitting point, it means that I am trying to split my tuples into different sets. For example, into subset D1 and D2. D1 is a subset of tuples in D where their values are less than or equal to the value of the split point, and D2 is a set of tuples in D where their values are higher than the value of the split point. So I need to define a measure to find the best split point. To find this value, minimum expected information requirement, I should turn back to slide 13 Here in slide 13, we define the expected information for a tuple in D. So we can use this equation for here. Or we should choose another method. If you think that this strategy is not good, you can choose another method. There is we have another method. We have another problem with ID3. In ID3, we use information gain measure, but it should be noted that this measure can be affected with the values with large number of values, with attribute with a large number of values. It means that if my data set, if my attribute is my data set is skewed toward the right or left, if my data is skewed toward the right or toward the left, information gain measure is not a good measure. It's affected by those large values. To overcome to this problem, in classifier C4.5 is a C4.5 is a successor of ID3. Instead of using information gain, scientists propose to use gain ratio. Instead of using information gain, we are using gain ratio instead of that. Gain ratio is a normalized value of information gain. In the past, in this lecture, we talked about normalization and why normalization is important in data mining. In C4.5 classifier, instead of using information gain, we use gain ratio. It's a normalized value of information gain. So, for example, if I try to find the split information for an attribute, I can use this formula, this equation here. And the gain ratio is this. Gain ratio of A is equals to gain of A divided by split info of A. So the difference between ID3 and C4.5 is using gain ratio or using information gain. And we can see that if our data set is biased and is skewed toward some large values in attributes, it's better to use C4.5 decision tree. Here, for example, for the last example, for our last example in the last lecture. Here we calculate the split information of income in dataset D. Here you can see that split information of D according to the income is 1.557 and gain ratio of income is 0.019. And now we can select the attribute with the highest gain ratio value. The attribute with the highest gain ratio value is selected as the splitting attribute. As we can see in C4.5 and ID3, if I choose another strategy to select the best attribute for partitioning, for new partitioning, I can define a new strategy, a new decision tree strategy. For example, in CART or IBM IntelligentMiner, CART and IBM IntelligentMiner are another types of decision trees. We have lots of decision trees. CART and IBM IntelligentMiner are two of those strategies. In CART, instead of using information gain or gain ratio, the scientists proposed to use Gini index. For a dataset D with n classes, the Gini index of D, dataset D, is defined in this manner. Gini of D is equal to 1 minus 2 summation of P of j in power of 2. Square of P of j. Okay? Where P of j is relative frequency of class J in dataset D. So we can use this measure. Okay. To split a dataset in CART, to split a dataset into dataset D into D1 and D2 to two different datasets, we should use Gini index using this equation and this equation. If I use this equation, I can say that if I select attribute A, for example, for a splitting, this attribute can reduce the impurity of my data. How much? Using the third equation in this slide, I can say that how much, if I choose attribute A, how much it can reduce the impurity of my data. I'm trying to make a decision. I'm trying to make a decision. So I should the best. I should select the best attribute. Which attribute is the best? The attribute that reduce the impurity of my decision higher than the rest. So reduction in impurity is important for me to create a card classifier. So I will select attribute A, where delta of Gini of A, attribute A, is the largest value among different attributes. The attribute with the largest reduction in impurity is chosen to split the node, to partition the tree. For example, if I choose, if I apply the Gini index calculation for our last example, in the last example we have two classes, 9 attributes, 9 tuples are in class by computers, and 5 tuples are in the class no. 9 of them are in class yes, 9 of the records or tuples are in class yes, and 5 of them are in class no. So the Gini index of attribute of dataset D is 0.459, and if I choose Gini index for income attribute, but look at this, the splitting point for income is low and medium. If I partition the tuples in D according to the income with values low and medium, I can calculate the Gini of income as this, and we can see Gini of income with low and medium is 0.4443. Hana, what is 14? Look at this. We are talking about this data set. We talked about this data set in the last lecture. In this data set here, we have 14 different records or tuples or rows. 9 of them has class yes, and 5 of them has class no. Okay. So if I choose, look at this, if I choose attribute income here, in attribute income, I can see that this attribute is a nominal attribute with 3 different values, low, medium, and high. And I'm trying to define a splitting point. I'm trying to find a splitting point for this attribute. I can divide the data set according to distance between income low and medium, putting the splitting point between low and medium, or between medium and high, or maybe between low and high. Here, we calculate all those approaches. If I choose income according to the splitting point between low and medium, it means that I'm dividing the income attribute into low and medium. Or dividing income into low and high, or dividing income into medium and high. I'm selecting different values for a splitting point. Okay? Here you can see that the Gini of income, when I'm choosing the space between low and medium, is 0.443. Between low and high is 0.458, and between medium and high is 0.450. Here I can see that if I choose a split points between low and medium, it has the lowest Gini value, and if I put it in this equation, I can see that it can reduce the impurity with the highest amount. So it's better for me. My best choice is choosing income with a split point between low and medium, then between medium and high, and finally between low and high. The Gini of low and high is the highest one. So if I put it in delta Gini, it will reduce the amount of reduction in impurity of my data. Okay? So it's better for me to use this attribute with low and medium split points. Here, again, I can talk about continuous values attribute, continuous valued attributes. If I use cart, it cannot works with continuous values. Instead of that, instead of using Gini index, I have to use clustering methods to split my data sets, to split all of data in my dataset into different parts. And then, according to those clusters, I can define some categories and choose. So, in ID3 and C4.5, if I try to use to works, if I try to work with continuous values, I have some methods to partition those values. But in cart strategy or cart classifier, because of using Gini index, it cannot work with continuous valued attributes. I should use another method such as clusterings to define those categories and then working with cart. Hannah asked me why income of low and medium is better than. Look at this. The Gini value for low and income of low and medium is 0.443. It's the lowest value among these three different Gini values. Okay? To find which of them is better than the rest, or which of them is the best, to find which of them is the best, I'm putting these values here. I know that the Gini value of D of a data set is a fixed value. Here, look at this. The Gini index of my data set is 0.459. And as I said here, okay, I have the Gini index of dataset D and Gini index of dataset D when I'm choosing a special attribute for splitting. The result is delta Gini of A, of attribute A. I should select the best attribute for a splitting point. But which attribute is the best? The attribute with the highest value of delta Gini. So the last equation in slide 17 should be maximum, must be maximum. Among those three values, I should select here, I should select the lowest value. Look at this minus here in this equation. I should select the lowest value among different values for different attributes to maximize delta Gini. To maximize delta Gini. Delta Gini means is a measure that shows the amount of reduction in impurity of my selection. So more reduction means more reduction in impurity means more clarification in my data. So the higher values for delta Gini is better than the rest for me. So I'm selecting the income low and medium. Okay. So until now, we talked about 3 different measures. Each of these measures has their pros and cons, or advantages and disadvantages. But I can say that if I choose information gain, information gain is biased toward multi-valued attributes. What does it mean? It means that if I have multiple values for attributes, I have some attributes, each of them has multiple values. Information gain affected by such conditions. The result, its result is biased toward those attributes. So in such cases, it's better for me to choose another measure. The second measure was gain ratio. Gain ratio is not a good option for unbalanced data sets. Why? Because gain ratio tends to partition my data into two splits with different size. One of them is too small and the other is too large. Gain ratio prefers to use unbalanced splits. So we should care in such cases. The third measure was Gini index. Again, this measure is biased toward multi-valued attributes and its calculation is hard when we have too many classes in my data set. But it's interesting that Gini index tends to use equal size partitions. So Gini index is affected by multi-valued attributes like information gain. It has some problems with data set with multiple classes. When we have too many classes in the data set, Gini index is not a good option. And Gini index tends to use equal size partitions. Here we can see that it's vice versa. It has it's against the behavior of gain ratio. In gain ratio tends to use unbalanced splits, but in Gini index, the Gini index tends to use equal size partitions. Okay, one more time. The disadvantage of gain ratio, information gain, is that this measure is biased toward multi-valued attributes. The disadvantage of gain ratio is that this measure tends to use unbalanced splits. A majority class and a minority class. A class with a few tuples and the other class has too many tuples. It's an unbalanced splitting. And the third measure is Gini index. The Gini index is affected by multi-valued attributes. Its performance is low for datasets with too many classes, and it tends to use equal size partitions. We have other decision trees with different measures. For example, in decision tree shade is one of the most famous decision trees, especially for, in management and financial cases. Shade is using chi2, square of chi2 or chi2 tests. For example, in CSEP strategy, in CSEP classifier, in some cases, the behavior of the classifier is better than using information gain and Gini index, or in geostatistics. Geostatistic is used a method near to chi2 distribution, and rest of them. So we have different decision trees with different measures for selecting attributes and also for splitting attributes. For example, I said that information gain and Gini index are affected by multi-valued attributes. The card tree has a proposal for this case to find multi-valued split points for an attribute. So maybe the last question is this. We have different measures for selecting attributes. Which of them is better than the rest? Which of those attribute selection measures is the best? It's hard to answer this question because it's completely dependent to the situation of my data sets. Generally speaking, I cannot say, for example, information gain is better than Gini index or better than gain ratio or Chi2 tests. I cannot say. Generally, I cannot say there is significant difference between them. So you can choose your measures using try and error methodology. Just you need to test different cases to find the best attribute selection measures. Okay. Last week, when we talked about ID tree, we talked about a very important problem, overfitting. And I said that overfitting means that I'm trying to use too many training records. So when there are too many records for training, the situation becomes complex. And in the tree, you can see too many branches and splits. In such cases, I can say that my tree is affected by anomalies, noise, outliers. If this happens, if my tree, my created tree, affected by anomalies, so the final accuracy of the tree will be low. It's accurate. It has a poor accuracy. During the test, we can see that its accuracy is very low. Why? Because my tree is trained based off various specific samples. And in such cases, when I apply an unseen sample into the tree, because of too many training, it cannot find a specific case near to the sample. So with the highest probability, the prediction of my classifier would be wrong. So overfitting can reduce the accuracy of my data. How I can avoid overfitting? I can overcome overfitting during the training. We have two different strategies, two different categories of strategies. The first one is pre-pruning. The second one is post-pruning. During the pre-pruning, Before splitting a node, we should make some calculation to find that, to answer this question. Is it good for me to continue the split process? Yes or no? So in pre-pruning strategy, before splitting, I should make some calculation and answer to this question. Is it good for me to continue this partitioning? In this case, I have to choose a threshold and split and calculate the goodness of partitioning for a node. If this, so I should define a goodness measure. Okay, I should define a goodness measure. Then I'm using that measure to find that is it good to partition or to split this node? If the result is lower than a threshold, I never continue the splitting process. If it's higher than a threshold, yes, I should continue the splitting process. In this case, you can see that we are working conservatively. We are working in a conservative manner. In the post-pruning, firstly, I'm creating the tree completely. Okay. Then after creating the tree, after finishing the tree creation process, I'm starting to remove some branches, to prune some branches in the tree. In this case, again, I should some measures to find the best points for pruning, because I'm looking for the best prune date tree. In C4.5 strategy, we are using post-pruning strategy. And you can see that post-pruning is simpler than the pre-pruning strategy, because here in this case I'm creating the tree completely and then just I'm pruning some branches in the tree. One more question is that how I can use decision tree structures for continuous valued attributes. As we talked in this lecture, if my attribute is continuous valued, firstly I should discrete those values. I should discrete the values into some defined categories. And then I can work with those discrete sets. So in decision tree, we cannot directly work with continuous valued attributes. Firstly, we have to discrete them into some subsets and then work with those subsets. We can use decision tree for handling missing data. In such case, we can use we can assign most common values to the attribute, or assign some probability to the possible values to the missing values. And in this case, decision trees can help us. And one more benefit, we can use decision trees to create a new attribute. Let's suppose that I have an attribute with some sparse values. Okay, I have an attribute with sparse values, so I can create a new attribute and I can put those sparse values into some limited number of categories. And maybe I have some attributes. I can create, according to them, I can create a new attribute. Instead of those attributes, I can create a new attribute. In such cases, instead of working with attributes with sparse values, I'm working with attributes with some predefined or some categorized values. So this can help me to reduce the fragmentation of data. This can help me to reduce the repetition of data and replication of data. Here you can see that we can use decision tree classifiers in different tasks, in different processes. We can predict the classes of data. We can predict missing values of attributes and data. And we can create attributes with higher accuracy. One more question. Can I use classifiers in large databases? As we talked in this course, today we have large databases. We have to work with big data or massive data. And as you see, to create a classifier, we need put lots of efforts. I should calculate, for example, information gain ratio or something like that for each of those attributes one by one for at each level of the tree. And also I should be care about the uh, overfitting and rest of the problems. In a large database, it's not easy for me to extend my classification strategies into large databases. We call it scalability issue. Scalability means that I can use a method regardless of size of input data. In some cases, some approaches, some algorithms are scalable. They can handle large input data, but not all of them. If a method can handle large data, we say that we say this method is scalable. Otherwise, we say that this method is not scalable. And this is one of the main issues when we are working with large databases, with massive data, with big data. Scalability is one of the major issues in such cases. Fortunately, decision tree approaches are very popular when we are working with large databases, with big data. They are faster than other classifiers. They are simpler than other classifiers. We can understand them easily. And also their accuracy is good. Based on my experience in data sets, different data sets, I saw that in most of cases, the decision tree classifiers can give you very good accuracy. They are standing uh, among the best and among the most accurate classifiers. So having a simple structure and fast um, learning speed while they have comparable accuracy for classifiers causes the decision tree becomes very popular. You can see too many decision tree classifiers. For example, we have a classifier rainforest. This classifier is especially works for works to create a decision tree structure with a scalability metric. To this, the rainforest strategy is using two different definitions. One of them is AVC set and the other is AVC group. The AVC set is used for an attribute X, and the AVC group is used for a node N. And here you can see the structure of AVC. AVC is a set of attribute, value, and class label. And here is an example for rainforest. I'm passing this example. You can read it after the class. Both is another strategy for scalability, to create scalability in decision trees. In this strategy, a statistical techniques called bootstrapping is used to create some subsets in the memory, and then for each subset we create a tree. So we have several trees, and then according to those three we construct a new tree. For example, new tree. This tree is very close to the past trees. I can say that the new tree is a resultant of the past trees. In this strategy, we need only two scans of database. The first scan is to create the small trees, and then in the second scan, I should check the structure of the new tree. So it's a good algorithm when we are using large data sets. Here you can see presentation for classification result, or the structure of a decision tree in different applications. Okay. The second method for classification is Bayesian base classification method. The base classifier is based on probabilistic prediction strategies. We can say that The base classifier is a statistical classifier. In this classifier, we should calculate the probability of membership in different classes. The base of this classifier is Bayesian theorem, and the simplest classifier based on Bayesian theorem is naive Bayesian classifier. This classifier has a comparable performance when we compare it with decision tree, for example, or with neural networks classifiers. Maybe one of the greatest advantage of Bayesian classifier is that this classifier is an incremental classifier. What does it mean? It means that during the time, this classifier can learn and update itself. So we can say that its learning process is incremental. During the training and maybe during the test, especially for stream data. This classifier can tune itself based on observed data. It can update its probabilities. And the overall structure of this creating this classifier is a standard. Here, okay, I will finish it. Here, this is the probability theorem, the total probability theorem, and Bayesian probability theorem. You have seen these theorems and equations in the past. So simply I'm passing these equations. I'm passing the basic definitions. Okay, it seems you have another class. Okay, I'm finishing or today's class until Tuesday. Please on Tuesday we will have a simple question from chapter 2. Please be care about the questions, the exam. It's a simple exam like the first chapter. Don't worry about the marks. Just do the exam. Read the textbook and do the exam. Also, I will upload the assignment 3. It's a small assignment.